Forget frequently asked questions.
Common sense, common knowledge, or Google.
How about advice from a real genius? 95% of people in any profession are good enough to be qualified and licensed. 5%
Go above and beyond.
they become very good at what they do, but only
0.1%.
are real geniuses. Richard Jacobs has made it his life's mission to find them for you. He hunts down and interviews geniuses in every field: sleep science, cancer, stem cells, ketogenic diets, and more. Here come the geniuses. This is the Finding Genius Podcast
With Richard Jacobs.
Hello, this is Richard Jacobs with the Finding Genius Podcast, now part of the Finding Genius Foundation. My guest is Irina Conboy, PhD, professor of bioengineering at UC Berkeley. And Irina has one of her lab mates as well. So I'll let him, Michael, do his own introduction. We're going to talk about what's called Therapeutic Plasma Exchange Treatments, TPE. So welcome, Irina, and welcome, Michael.
Thank you for having us.
Hello. Yeah, hey, Michael, if you can give a brief bio introduction of yourself as well, that would be great.
Sure. My name is Michael Conboy, PhD. Been working with Irina on the greater question of aging for 20 years now, since we were postdocs.
Okay, excellent. Well, tell me a little bit about what is a plasma therapeutic exchange? What is it and when is it used? We'll start there.
So do you want to know applications to aging or what this procedure actually is?
Yeah, first, what is the procedure? What is plasma exchange? And then what are its uses?
Yeah. So therapeutic plasma exchange, or TPE, has been in clinical practice for over 30 years. And what happens is that patient has two IVs, and then through one IV, they're pretty much bled to they lose like 70% of their blood. But they're not dying because through the second IV, they are simultaneously infused with their own blood cells resuspended in saline, which is just salty water, and albumin, which is the most abundant protein that we need. So as the result, the liquid component of blood becomes severely diluted and replaced kind of with the solution of salty water and major carrier protein. So as you can imagine, this procedure can be used for treating a variety of autoimmune diseases just to throw away circulating antibodies that might attack patients' organs. Or when there is drug overdose, you kind of wash away the drugs from the blood system. So that's how it was used traditionally.
You mean it's essentially to dilute, negative compounds in the blood through this plasma exchange? Is that how?
Exactly. So you can simplify, summarize it as to dilute something that is pathogenic in your blood. Pathogenic.
So you can, obviously you couldn't like put water in someone's veins because they would die, but plasma is maybe like an analog to increase blood volume in a way that doesn't cause negative effects and dilutes potentially negative compounds in the blood.
There is no plasma. It is just salty water called saline.
Okay.
It's physiological saline with added albumin, the major carrier protein in blood. But
it's all like
purified.
But what about red cell capacity? What about hemoglobin? Do you also have to add that, or like what would happen if you got a very significant amount of saline? How would your blood chemistry change potentially for the worse?
Yeah. So what happens is that you have cells in your blood, and you have liquid part of the blood. So the cells are not thrown away; they are actually spun down and made into a pellet, and then they resuspended in those saline albumin solution and returned back to the patient. So you can look at it as a separation of liquid part of blood from cells in the blood. Liquid part is the only thing which is discarded and is replaced by completely chemically defined, just like salty water with the purified protein, and then cells that all go back to the patient simultaneously with the patient being bled.
What's responsible for plasma production though? Like, again, if you drain out the liquid component, you put back all the cells, which I now get, you put back saline and albumin, but the plasma portion, what reconstitutes it, and what would happen in that intermediate stage when you have very low plasma, relatively versus the normal amount?
So that goes to the question, what is plasma? What do you think is plasma?
That's true.
let me interject a little bit here. So you might be familiar with donating blood. You go to the blood bank, whatever. They put one needle in one arm, and you sit there, you squeeze the ball or the thing for a while, and bing, and then the bag of blood is full. If you do that for a while, sometimes they'll ask you back and they'll say, well, can you donate platelets? Or if you go to one of the plasma donation centers, they say, can you donate plasma, right? So there they hook you up with the two IVs like Irina described, and it goes into the machine, and you can set those machines up to separate out and remove or add back any of the major components of blood. So you have the cellular component, which would be the red blood cells and the white blood cells, and then there's a kind of a small cellular component, the platelet component, that those are involved with as we know, for clotting, right? Clot the blood. And then what's left over, that liquid is the plasma. So that's a mixture of
proteins,
right? Proteins, electrolytes, right? Salts, antibodies, and of course the clotting factors that the platelets trigger to form a clot if there's an injury or something like that, and you need to clot the blood. So what the machine does is you set it. In fact, I think these days the plasma exchange machines, they use a lot more membrane filtration than they do centrifugal spinning of cells or particles out of the blood. So the plasma goes through a membrane, the cells keep going and get infused with, caught in a stream of incoming physiological saline with this major protein that's in the blood, albumin. And albumin, we think of albumin as being like, egg white protein or something in chickens. That's everybody's familiar.
Albumin over medium with some bacon and a toast too.
Right. So but the major protein in most animals' blood that's not a cell is this albumin protein, right? So that so that the body, if you're going to remove a lot of the plasma, you need to add back the albumin. Otherwise, the body can go into kind of a certain shock, albuminemia, right? It means you're low on albumin, because it does some other stuff just besides like making the blood kind of slippery.
Blood vessels plump.
Yeah, it keeps the vessels plump and does osmotic stuff too. So that's how this
procedure works.
Procedure works, right? So, but in that, the part that gets thrown out, the plasma fraction that gets thrown out, there's the old albumin that was in the body. Anything bound to that albumin, antibodies, and a lot of the signaling factors that travel in the blood, right? So,
yes,
growth factors, hormones, that kind of stuff, gets thrown out too.
And that is thrown out.
One question here, the albumin that you put back, if there's an excess, I would guess that might put more load on the kidneys temporarily, or do you put back, essentially about the same amount that was there? And is there any other downstream effects of this?
All that is calibrated. There are centers that see 100 patients per day and perform this procedure, as I mentioned, for 30 years. It is not novel procedure. And everything is already well-known and calibrated to basically restore the liquid composition of blood as optimally as possible. And the idea is that if there is some circulating protein or factor or antibody that are causing problems to the patient, we physically throw them away. That is the main idea of this procedure.
So what are the effects of doing this? What conditions would people have, whether they would use PTE, and how does it help?
So TPE, therapeutic plasma exchange, is, for example, used for recipients of liver transplant or kidney transplant or any transplanted organ where they start rejecting the organ when they do not take it well or receive it well. And by doing this procedure, then the harmful antibodies which are attacking transplanted organ are physically diluted because we throw them away with the plasma. So that's one approach. Another close approach is autoimmune diseases, for example, lupus or multiple sclerosis, kind of the same idea. Another approach is drug overdose, when people just overdose on drug and the drug is still in their bloodstream. So we can throw away the plasma.
How do you get rid of that?
You
throw out the liquid part where the drug is floating around in there, but you got to replace it with some liquid. So you replace it with this.
Is that what it?
Yeah, it's like you could call it like a reconstituted plasma, but it's not even. It's not as complete as plasma. It's just the albumin. And
so your plasma analog, yeah. It doesn't have gamma globulin, I guess, or
exactly right.
Exactly. Yeah.
They'll often add gamma globulin, which is mixed antibodies, so that the patient has some circulating antibody. Just either not, but they won't be, those antibodies won't be against the whatever the immune rejection that's going on, or the autoimmune disease. Presumably doesn't have any. It's just antibodies and have drugs in it.
And some physicians do it, other physicians do not do that.
Okay, so all right, so if there's a drug that's affecting you negatively, I understand. What about just as an overall anti-aging therapy? How and why does it work?
Yes, so the best analogy is to compare that procedure with changing water in a fish tank. So you have a fish tank, and it was there for a while, and there are various chemicals and byproducts from fish eating and pooping accumulated in that fish tank. And then the water becomes really bad for their health, but if you just replace the water with a fresh one, things become better and how we call it, more homeostatic.
A lot of good stuff for algae to grow.
Exactly.
Like that, but not good for the...
But not good for it. Or changing oil in a car, right? At some point you need to change oil, everybody understands it. So what happens to our bodies is that as our tissues become damaged from various processes that we experience over the lifespan, then the cells in these tissues start overproducing certain factors. Interestingly, aging is not really a decline, as many people think, like we need a vitamin. It is actually excess of many factors that when they are at good levels, they are really very good for us. When they are at bad levels, they become counterproductive and harm us. And so then therapeutic plasmapheresis physically reduces their levels and calibrates things that circulate in our bloods to their younger state. And that rejuvenates a bunch of organs and systems, including the brain.
Well, I've had infusions before, they do like B vitamins and, a bunch of stuff. You go to these clinics and they'll do like an infusion, or, they'll come to your house if you're hungover, that kind of thing. But they're not taking out the existing plasma. They're putting in saline with, so how much of an improvement is it to take out the existing plasma and then put back in, this plasma-esque saline type solution?
It's literally like game changer, because with respect to infusions, you cannot imagine that you have a cluster of decaying bananas and you throw one good banana into this cluster. This is infusion. You have decaying fruit and you throw one good piece of fruit. It's not going to change anything. You need to remove the rotten fruit. And then what actually happens, I don't think that we need to add useful factors back, because they did not disappear from our genome or blueprint. They're still there, right? We have them encoded in our DNA. They were simply suppressed or inhibited by those aging elevated factors. So when aging elevated factors are physically diluted, all of the good stuff is coming back naturally and safely at the levels like when we were in our mid or late 20s.
For aging, this is still at the experimental stage for people.
Well, Irina, is this how you got to be 400 years old? I'm just kidding.
I don't think so. I think that's how you get to be healthy and capable and useful looking, good looking for additional decades. So right now, we think that we are...
I was just teasing you. It'd be funny if you had a shirt that says I'm 300 years old or something.
I see, yeah.
ITPE.
That is an awesome idea. Yes, maybe I should do that. I should be more realistic, maybe like 125 or something.
There you go. But go ahead, I'm sorry. I was just making a joke.
Yeah, so basically, we imagine that, a couple hundred years ago, before we knew about antibiotics, we thought that 40-year-old person is very old, and they were physically much less fit. Now, 40 is like when many people start their scientific careers. So what is going to happen, in my opinion, with meaningful rejuvenation approaches is that it will be the same, but now instead of 40, it will be like 70. 70, you are still very fit, you are competitively playing tennis and golf or what interests you, and you are thinking maybe I will start new career or get PhD in additional discipline.
So are you guys doing this protocol? And when someone goes on it, how often should they get this done? And, what will they experience right after getting it, maybe for the first couple of days afterwards?
You would want to talk to someone who actually does this procedure on patients. We could refer you to a collaborator we had on the paper where we published this stuff, which is Dr. Dobry Kiprov. He's in Mill Valley, California. We work with mice, right? So we don't.
That's not true.
We get samples from people and we look at them and see what happens, change in the blood. But we're not MD doctors, so we don't.
Yes.
No, but have you guys had it done to you?
Not yet.
We have not done it to us, but I can actually elaborate why not. Why we decided, at least for now, against it, is because we published several papers where we show that people, not mice, but people who had this procedure done by Dr. Kiprov had significant improvements and rejuvenation in their cells in the blood. So the cells in the blood become younger and their immune system is working better. And anecdotally, they say that they have more energy and kind of feel younger, right? But they are starting as already relatively healthy people. And this procedure has been only tested on patients. So it is really a treatment. And so there are also some side effects. So the question is not like, we just missed this point, then why don't we all go in and have our blood removed and plasma diluted? The question is, are the positive effects or benefits are more than the potential negative effects? If not, then I would not recommend doing that.
Well, what are the negative effects that you've seen so far?
Yeah, so it's not us, it's actually the negative, because it was already in clinical practice for like decades. So one of the negative effects is that the cells, when they go through the machine, they become damaged. And when they return back to the patient, they trigger all kind of unhealthy responses, including damage of the kidney and liver. And
wow.
Yeah.
But this is my understanding that the incidence of this is low, like less than 1%.
Well, have they gotten better centrifugation techniques? Like there's a whole field of exosomes or extracellular vesicles. They're incredibly delicate. So I would guess that this would benefit from learning from that field, because they've had to come up with very sensitive processes in order not to tear apart, all the exosomes that are being harvested and collected. So that would probably make this a lot safer,
No, they have not made it safer, because what happens is that you have a cell. Exosome is like tiny vesicle, and you don't care if you damage tons of them as long as you have enough of them that are in good shape.
They'll be fine going through the machine.
Exactly. And they're like, much, much smaller.
Platelets I'd worry about.
Yeah, but there are the cells that we have, like red blood cells particularly, and platelets. When they become damaged and then return to the patient, it's not just that we don't have functional cells, it's that the body of the patient perceives it as some major problem, and it tries to activate immune responses, and then also tries to get rid of those damaged cells, which puts lots of load on kidney and liver. And what Mike mentioned is correct. It's, I would say, less than 5% chance, and maybe in that case
says less.
And for some cases, it's less than percent. There are a bunch of side effects that are like listed. There's also embolism and other things I forgot about them. I think that the damage and return of damaged cells back to your veins are probably the most problematic. But if you think about it, if you do procedure once, you are not going to get younger. You need to do it repetitively. And then every time you do it, that 1% can eventually materialize into something bad.
But okay. I mean, there must be, if you said it's been around for decades, there's got to be techniques to reduce the damage to the cells, to reduce the side effects. There's got to be.
No, because what happens is that they come in touch with plastic. I mean, I am in the bioengineering department.
You'll want to talk to an MD who does this.
Okay.
Have the most accurate numbers on the incidence of complications, and in their practice what they find.
Exactly.
Right?
Exactly.
Because I imagine, like a lot of things, there's probably people and institutions or locations that are good at this, and there's probably a couple of people who aren't so good at this.
Right. So what I was going to mention also, when you talk to a physician, try to find a physician who doesn't have financial conflict of interest because they charge thousands of dollars to perform this procedure, because if they do, their opinion could be influenced by that. Because right now, yes, after we published our papers, it became kind of interesting to many people and many physicians. And so I just would like everybody to think about it carefully and talk to their primary care physician before deciding on doing this procedure.
Well, you said that you're doing it in mice. So are there much side effects in mice, or is it, because they're different, you don't really see any?
So what is important probably for your audience to understand is that when we do it in mice, we just do it once, and then we basically then euthanize the animals, and we then look at what happened to their organs. We do not do it every week or every other week, like, for example, some clinicians are prescribing to people. So,
I was going to ask how often is it recommended, and how often is too much versus, not enough?
We don't know yet. So I think very, very important next step would be to do really well-controlled clinical trials that are unbiased, and patients or people are randomized. So they don't even know if they have mock procedure or they had actual plasma dilution, so there is no placebo effect confounding the outcomes.
We saw changes in the blood proteins and in the blood cells within 1 to 3 procedures.
About 1 month apart.
One month apart. In the mice, we saw within a week after doing the procedure that there was dramatic rejuvenation of muscle, liver, and brain. So, and I could see doing this myself if I was going to have some sort of a another procedure or surgery or whatever. I was in an accident or whatever, and it injured my muscle or my liver or my brain.
Yes, exactly.
I'd say, maybe this would be worth it. The 1% risk or whatever, it would be worth it to me. But that hasn't happened yet. So
yeah. Exactly. That's very well put. But not, when you just want to, competitively be in MMA, whatever it is, in the mixed martial art competition, and you are now pushing 45, and you want to compete against younger opponents.
Up your game.
Exactly. I would not recommend it. No.
How much plasma is exchanged in a typical protocol? Like, could you do a reduced amount and therefore there'd be less damage?
That is, first of all, yes. The answer to this question, there would be less damage if less cells were taken out and then go through the filters. Because whenever cells actually touch plastic or anything that is present in the machine, that damages them. So it is not easily. So,
but what happens when people donate blood, though? I mean, it goes into a plastic bag, and sometimes it gets centrifuged, sometimes it doesn't. I mean, maybe it always does. How does it get transfused without hurting the person it goes into?
Because they have like tiny percentage as compared to the therapeutic plasmapheresis or TP. So TP removes over 70% of your blood. 70%.
I see.
Of plasma.
Of plasma, but then that means that the whole blood went through the machine.
Well, the blood has to go through the machine probably 10 times in order to get 70% of the.
Exactly, and it has to go through.
It's not 100% each. It's not 100% efficient each time it goes through the machine. So people do plasma donation regularly. There are plasma donations. There's one down the street here, right? Where they'll take out, whatever, liter or something like that, a liter or two of plasma. I don't know, maybe that, but and that's the same. Essentially the same machine, right? So, so this type of they don't add back albumin; they just add back saline when they do that, because they're not taking enough to cause the albumin. So that the technology and the expertise is there, right?
And many people are interested whether donations of plasma or blood would be sufficient for rejuvenation, and we do not know that yet because, as I mentioned, there are certain aging elevated factors, and it is not given that simply reducing them by a little bit is enough, because they feed to themselves, they basically induce their own production And it is quite possible that unless you drop the level below a certain threshold, nothing good will happen. But it is
Okay.
and we do it a little bit and with less side effects and still achieve the desired rejuvenation. That has not been yet done. And certainly.
Well, by the way, there's at least one high profile person that's doing this, which is Peter Diamandis, the founder of the X Prize. That's how I found you guys. I saw an article where he had done this, and then some of the scientists involved, were you guys amongst others. So that's why I contacted you. But at least he's doing it, so he might be a good guinea pig to see if he's okay or not.
So is he doing blood donations to see if he is better? What is he doing?
Oh, I don't know, but I do know that he's doing the this protocol. He's done it several times at least.
Yeah.
He's welcome to contact us. We'd be happy to hear whether it's working well for him or not.
Exactly.
Yeah.
And by the way, there's Brian Johnson who was doing things of that nature. And there is the whole retro bio with Joe Batla-Cross, right? Who we know, and we discussed this procedure with him, and he decided to solicit like $100 million or so to develop it. But I can tell you, kind of in broad strokes or general terms, is that I don't think that unless there is a major bioengineering breakthroughs, that this procedure will be safe enough to basically go every month and have your blood mostly removed, like almost all of your blood removed, and replaced with saline, and your cells return back, and you become healthier and younger.
How about once a year? How about in spring?
Once a year, absolutely. Once a year, maybe.
Again, why not do just a lesser amount? If you're doing a high percentage of your blood volume, do a third of that, and then do 1/4. Why not do that instead?
Right.
So imagine that you are changing oil in your car and you decide to change 1/10 of the oil. It's going to keep your car in good shape.
It will. I mean, so here's where the car model and the biology kind of separate, right?
Yeah.
So in a car, you could probably get away with changing the filter and 1/4 of the oil every couple thousand miles, and in the end, it's the same amount of changing and same amount of fresh oil that if you didn't know what is it in cars these days, they're probably up to like 10,000 miles, like 5,000 miles. But in people, what we saw was what it looked like a resetting or a rebooting of the signalings, the signals that are in the blood. So it wasn't that we removed plasma and therefore lowered all the signaling protein, and then when the body recovered from that, those signals stayed low. No, some stayed low. A lot of them went back up to normal levels, and some went up to high levels, and those were the high levels that they would be when you're young. So it was almost more like a rebooting of a computer than a.
Mm-hmm.
And I don't know how much blood or how much plasma has to be exchanged or removed and replaced in order for this effect to take place.
What have you guys looked at the removed plasma and analyzed it, gas chromatograph to see what kind of compounds, what levels? I'm sure it's a very complicated substance with lots of stuff in it, but has it been very well characterized? And therefore you might get some idea on what's building up, what specifically.
It's all in the paper. We have very good idea about it. It is, hardcore science. I don't think it is for the popular podcast, but it has been characterized and there is certain understanding. But I would like to give you another analogy or metaphor from a movie Fly. Remember, there was like the scientist and he developed teleportation device. Have you seen this movie?
We've all seen it.
Yeah?
The Fly. There was.
The Fly with Jeff Goldblum. I remember. Yeah, I remember.
Yeah. So it is perfect. I think perfect metaphor, because first he was not worried when his computer told him that he merged with the fly, because he thought that he just absorbed the fly. The fly is so much smaller than him. But then it turned out that they merged at the genetic molecular level, and then he was in trouble. So what happens with therapeutic plasmapheresis is that we are resetting an organism at the genetic molecular level. We are not simply reducing the level of aging elevated factors in blood. If you did that would be really ineffective, because the old body would reduce enough of them again in a couple of hours. But once we reduce them enough, then the whole system is reset at the genetic and molecular level to a younger state. And that can last for about a month. And if you did not remove enough, there will be no resetting.
We don't know for sure how long it lasts, but it's at least a month.
Well, you don't know what the trigger is, like the level needed to, the minimum dose in order to trigger this resetting.
In mice, that might, because they're all genetically the same and they live in the same cage, and it might be the same for individual mice, but for humans, it might be very different between different people.
Exactly. And to tell the truth, it's not that we don't know that at all, right? We are scientists after all. So if we know enough to at least have some predictions or expectations. But once again, well-controlled clinical trials would be instrumental to what you are saying is correct, is to actually know that. Instead,
what would be interesting is if you took some of the mice up to altitude, to Denver, Colorado for a month, they would produce, I guess, more red blood cells. And then if you did this, I wonder what would happen, because there would be more, theoretically, I guess, more red blood cells. Would it mitigate the damage? Would it increase the damage? It'd be interesting to see that possibly.
In general, it's kind of interesting, right? But it would be a confounding effect, because what we are doing has nothing to do with cells in the blood.
Well, yeah, because
and certainly not with red blood cells, because red blood cells are actually, interestingly, right? You would think that red blood cells also become old, but in our old mice or in old people who had this procedure, it is their own old red blood cells that were returned to them, but they were still younger because a bunch of small molecules and factors in plasma were now diluted.
Right, but you said that the cells that are there get damaged. So if there's more of them in the first place, I wonder what the difference might be.
I think more of them will be damaged. It is not that.
Maybe.
And I would object to the damage thing. I don't think there was enough damage of the cells to be a serious concern either in the mice or in the plasma free. I think there's a low risk for some people doing therapeutic plasma exchange.
Well, the reason why I say this is maybe to make the protocol even safer. I'm just totally speculating. The recommendation might be to spend X amount of time at altitude to increase your red blood cells, and therefore it makes it safer. I mean, I have no idea if that's the case. It could be the opposite, but it's just a thought that came to mind. That's all.
All of it, right? All of this is kind of next steps.
You're a systems scientist. Yeah.
Yeah, exactly. Thanks for brainstorming with us on that. In my opinion, it's not that, we don't have enough red blood cells after procedure. Is that the ones which were damaged, again, I'm kind of insisting that some of them will be damaged by going through the machine, will then trigger responses of the body to say that something went wrong. And it's not a big deal. It happens infrequently. So if people want to use it, at some point they can do it. Yeah.
I know you. I'm sure you guys. I'm sure you probably don't have the answer, but another thought came to my mind is: has anyone ever done infusions or transfusions in a hyperbaric chamber? And I wonder what that would do. I know it's we're kind of getting off in left field, and I'm sorry, but it just came to mind. That's all. Just something to think about.
Hyper meaning that it's high pressure.
Yeah, high pressure, like a hyperbaric chamber. Let's say it's I don't know what they go up to, but an extra atmosphere or something, and maybe 2 atmospheres instead of 1. Because it drives oxygen into the tissues more, supposedly. So I wonder if you're getting an infusion of something, how that would be different.
I don't know. I remember reading a paper that was supposedly increased perfusion to various tissues and like the brain and stuff that was supposed to be good, but I don't know anything about it.
Exactly. We are not like experts, right? We don't know what that would do. What I can tell, you and your audience kind of, again, broadly, generally speaking, is that once again, before we knew about antibiotics, people who had tuberculosis were taken to high altitude and the pine forest, and that really helped them. But it did not help them to the extent as penicillin, and it was not really a breakthrough that patients were looking for. And so what we are looking for is the antibiotic against aging, not the accumulation of various small improvements that can still be very important and help people today, but it will not be a breakthrough that would allow them to remain functional, healthy, youthful looking until they're, when they're in their 70s or 80s.
Gotcha. Well, very good. What's the best place for people to keep tabs on your guys' work, as you go along? Where can they go?
PubMed.
Well, they can, they can get in touch with Mike and me. We run Conboy Laboratory together. through just getting on UC Berkeley, University of California, Berkeley directory and entering my last name. And then they will get my email address. Or if they want to know what we are up to, yes, they can look at our publications. Again, Google our last names. It's the same last name. And Mike and Irina and aging. And you will find a bunch of highlights about our work, press releases, as well as primary discoveries.
There's a website. Excellent.
Yeah, we have Conboy Lab website.
Okay. All right. And so the best place probably is, like you said, PubMed, search for Irina Conboy and Michael Conboy, or go to UC Berkeley and you'll be in the directory and the lab will come up as well, right?
Or just do Conboy Lab on Google, and Conboy Lab will take you to our laboratory website. And there are our projects, our papers, our patents, all kind of stuff.
Very good. Okay. Well, both of you, thank you so much for coming on the podcast. I appreciate it.
Thank you, Richard. Thanks for having us.
Yeah.
Have a good weekend.
If you like this podcast, please click the link in the description to subscribe and review us on iTunes.
You've been listening to the Finding Genius podcast with Richard Jacobs. If you like what you hear, be sure to review and subscribe to the Finding Genius podcast on iTunes or wherever you listen to podcasts. And want to be smarter than everybody else? Become a premium member at findinggeniuspodcast.com. This podcast is for information only. No advice of any kind is being given. Any action you take or don't take as a result of listening is your sole responsibility. Consult professionals when advice is needed.